When we're examining a molecule to determine how many signals it's going to give in the proton NMR, we need to consider several things. One thing we need to know is that unique hydrogens are going to give their own signal in the proton NMR. So if we just look at this molecule here, at first glance it looks like we're going to get 4 signals. One from these 3 hydrogens here, one from these 2 hydrogens, one from this one, and one from this one. But let's take a closer look. One way we can determine whether hydrogens are equivalent or not is to take them off and just replace them with an imaginary group. We'll call it Z. So from these hydrogens on this last carbon here, I'm going to put my imaginary group Z here. I'm going to fill the rest in with hydrogens. Same thing with this other one right here. I'm going to put my hydrogen here. This time my imaginary group is going to go here, and my last one's going to go there. Same thing down here, Z, hydrogen, and hydrogen. Now, as you can see, all of these are equivalent because we can rotate about this bond here and make any of these equal to each other. So these 3 hydrogens are all equivalent, and therefore they're going to give one signal in the proton NMR. And when they're all the same, we call them homotopic hydrogens. So for these next 2 hydrogens, we're going to do the same thing, and we're going to put an imaginary group right here, Z, and we're going to put our hydrogen here, and the opposite down here, Z, and hydrogen. Now you can see these 2 are enantiomers of each other. Now when it's like this, we call these hydrogens enantiotopic hydrogens. Now under normal conditions in proton NMR, they're going to give just one signal. But if we use a chiral solvent, then we're going to get 2 separate signals. So we'll look on these last couple of hydrogens here. This hydrogen right here is unique, it's by itself. But what about these 2 over here? Where I'm going to put my imaginary group here, Z, and my other one right here, hydrogen, and the opposite here, hydrogen, and imaginary group. Now you can see these are diastereomers of each other. This imaginary group is trans to this hydrogen right here, while this down here is cis to this hydrogen right here. So we call these diastereotopic hydrogens, and these will always give a separate signal while they're in the proton NMR. So let's recap. Coming back over here to our original structure, we're going to give one signal here from these 3 hydrogens, one signal here if we use an achiral solvent, one signal from here, and 2 signals from here. So we're actually going to get 5 signals, not 4, in our proton NMR.